Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah wassalatu wassalamu ala Rasulillah. Amma ba'du. Alhamdulillah, in this moment we can continue our discussion in this morning. And for today only, we are studying in 7 o'clock. And usually we are studying in 11 o'clock. All right. And then we continue studying. Let's begin with praying together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbalan. Allahumma inna na'udzubika min ilmin la yanfa' wa min qalbin la yakhsha' wa min nafsin la tashba' wa min da'watin la yustajabu laha. Rabbana zidna ilma warzuqna fahma. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Amin. In the past meeting, we are studying about persistent segmentary, and most of you already got accepted on problem A, and also some of you submitted problem C and E. All right, congratulations, and good job. And then in the past meeting, we also discussing about problem B, and I got another simple solution about the solution for this problem. This problem is for types of operation, and in order to handle the last type, we can use persistent segmentary. And then in order to handle the first and second operations, we can use a segmentary, and the size is only nm. And don't worry, we don't need to make the n is equal to the power of 10. No need to change the value of n, just n times m. And each of them only storing 0 and 1 or 2 and false without storing anything. And we don't need any operation. We just need to store a persistent array. But if you store it as a sum or anything else, it is up to you. But we just need to know a value of each position. We don't want to do range query in this segmentary. All right. After that, in order to handle the third operations, we will create another segmentary with size m. What is m? Okay, sorry. I think the number of cells, which is n. All right. We just need to store n, and we are storing the number of book, and also is it inverted or not? If inverted, so storing the value and true or the value and false. So we are storing two values. All right. Okay. And then the operation used in this segment tree is just the sum of the first, like this. So if here 8 and true and here 6 and false, then we need to store the sum. All right. So in the root of the segment tree, we got the sum or the total number of books. Okay. All right. So the point is we will store two array of Boolean, persistent array of Boolean or true false, and then we are storing a persistent segment tree using sum. For the second segment tree, the purpose of this is to store whether that self is inverted or not. If this is inverted, so the value is true, but if not inverted, the value is false. Okay. So so the main function is like this. For example, we got some value. We have some trees. At first, book and max q versions, and also is it inverted or not, and then the sum. Right. Initially, both of them is 0. When we build the segment tree, all of the values is 0. And this is a sum segment tree. All right. And then after we got the input nm q, nm, and also q, then we will create a book 0 equal to new trees with size n times m. All right. And then after that, we also need to build the invert array with size n, and also sum with size n as well. Then we don't need class, right? There is no. This is for problem A. Okay, and then there are 4 types of operations. In the first operation, given x and y, and we will check whether x and y is true or false. So we will make it true. So if it is initially false, then it become true. But if it is already false, then just make it still false. Sorry, if it is initially true, then just leave it true. All right, so we need to check whether in that position is true or false. Okay, sorry, I think I disconnected. So let me off my video in order to reduce the bandwidth. All right. So after we build all of the segment trees, then we will make the first types of operations. And in the first operation, we will check if the book is false, then change it into true. But if it is already true, then just do nothing. All right, so we have to check first whether the book, okay, and since this case is, sorry, this segment tree is persistent, so we need to use this. This is just O1. Okay, thank you. And then we will query. Okay, maybe some of you can also make the second query, because if you can guess the solution. All right. We will query in point x minus 1 times m plus y. Is it correct? Yes, I is the index of the self, and itself consists of m books. That's why we will multiply it by m, and you know x is one index set, so yes, you can create a hash function. Okay, so we can use like this as well. Yes, x and y. Yes, that's correct. This is point query, so the complexity is just O log n. And then we also need to XOR, use XOR with the invert step. Is it inverted or not? So we will check is the x self is inverted or not. If inverted, then we will XOR it by 1, which is changing this into the inverse. All right. And if it is true, then just leave it, just ignore it. Just do nothing. But else, or we can also make it like this. If the result is same, so false and false or true and true, it means there is no book there. That's why we will make it true. So we will update point, and in order to update, We will use this since the segmentary is persistent. And then we will update in point hash xy and change it into 1 minus inverse. Do you know why? Okay. Is it understood? We will change this index into this. Or we can store the value here since we will use it twice. Okay, you got it? All right, that's great. And then using the same way, we will make the second query. All right. And then don't forget to increase the sum. So sum I is equal to sum I minus 1 update in x by 1. Or let's differentiate the function between add and update. Update means changing the value become like this, but add changing the value become like this. All right. So update means changing a value like this. Sorry, this is add and update is just like this. All right. After that, let's do the third operation. What shall we do? We will do we will inverse the array inverse x inverse I equal to inverse I update is. I think at first we need to query the value, and then when we update it, we will change into 1 minus a. Is it correct? Yes. Yes, thank you. And then how about sum? The sum is also updated, which is updated by the query of sum. Yes, that's it. We will make it m minus b. Okay. Okay, that's correct. Is it understood? And then in fourth operation, what shall we do? We just need to make one line plus input x, and then what shall we do? Okay, three lines, I think. Inverse I equal to inverse x, that's it, and also bookend sum. All right. Okay, great. Good job. And then what is the output? The output is just sum, yes. Sum. Yes, that's correct. This is O1 since we just need to access the value of the root. Okay. I think the solution is simple. And the complexity is just O Q log N. Yes, that's it. All right. Here, there are just 3 persistent segment trees. Okay, isn't there any question for this problem? So let's continue to the next problem. And Faisal got accepted here in this problem. So the idea is we can sort the station based on R. Okay, so let me explain the brief description for this problem to remind you the question. Okay, so given an stations, each of them has some values, which is X, R, and F. And a pair of stations is bad if the distance is like this, or just satisfy two condition, this and also this. All right, so we will find the number of pairs satisfying these two conditions. Okay, so at first, in order to handle the second condition, since we know that the value of k is so small, so we just need to create each segment trees, or actually we can use Fenwick tree as well. If you don't want to code segment tree, then just code Fenwick tree. It is much simpler. Okay, so it means we have to create 10,000 Fenwick tree, isn't it? How to create some Fenwick tree? And in order to create many Fenwick trees, we can create an array of vectors. So its vectors can have different size. Okay. So because k is so small, so we can just check one by one. You can use flying table. Yes, maybe. Okay, yes, maybe there are some another solutions. All right. So if there is a station with frequency f, then we can query from f minus 20 until f plus 20. Sorry, f minus k until f plus k. So the number of curies is 2k plus 1. Okay. So the complexity is nk log. Alright. And then how to handle this? In order to handle this, at first we can sort based on the value of r in non-increasing order. So from the biggest one to the lowest one. So this is from the biggest r until the lowest r. And then we will update one by one to the Fenwick trees. The Fenwick tree just storing 0 and 1. 1 means already activated, but if 0 is still non-active. Okay. So because we are activating each station one by one from the biggest R, so each time we check a specific station, the value of R is less than or equal to all of the activated radius or radius stations. Alright. So the value of minimum R is equal to Ri. Alright. And then we want to find the number of activated radius using queries in Fenwick trees, which is because station I is in Xi, so we will query from Xi minus Ri until Xi plus Ri. Okay. Is it understood? Do you know how to do range query in Fenwick trees? Yes, okay. How to do range query in Fenwick trees? Okay. Yes. Actually, Fenwick tree can only query prefix. Is it correct? Okay, yes, that's correct. Since the operation is just sum, so we can do inclusion and exclusion just like prefix sum. All right. And then how about the non-activate stations? We are no need to check them since we will check it at next in the next iterations. So in this iteration, we just need to check how many pairs so that I is in the rank of the pair. All right. So the other pair will be counted in the next iterations. All right. And Saram said we need to do compression, and that's correct. We need to do compressions not only because X is too big, but we will create 10,000 Fenwick trees. Is it correct? if we are not compress them, so the complexity is the number of Fenwick trees times the maximum x. Even x is only until 10 to the power of 5, we still need to do compressions. So the size of the Fenwick tree is small. The size is equal to the number of frequency equal to I. All right. Okay. Okay. And then how to compare the value after compressions? Then we need to do binary search. Or just binary lifting. We will find in the compressed values. We will find the biggest value that is still less than or equal to this until the biggest value that is still less than this, strictly less than this. All right, that's it. So until this point, is it understood? Mm, okay, yes, you can use drawing table. Yes, that is also correct. But how to handle minimum R here? Which is first, I think your solution is correct. If we use flying tables, I think every time we need to create a new frequencies and then update all of the values there. Is it correct? Or you use different ideas? Okay. Can you explain to us how to handle these values? If we are already create all of the frequencies for f minus k until f plus k, and then in the next iteration we need to create another Fenwick tree. Is it correct? And we don't use this again, so we can just replace here. But what shall we do in the Fenwick trees? In which index we want to update? Okay. Right. Yes. Yes. So we repeat the insertion. Yeah. Yes. So you reset all of the Fenwick tree. Is it correct? Reset all of the Fenwick trees, 2k plus 1 Fenwick trees, and then add one by one from the biggest R. Alright. Yes, that's also correct. So the complexity is for each values, it is updated 2k plus 1 times. So the number of update is around onk, and the complexity to update is just log. And the log is so small since the number of log is the frequency or the size of Fenwick tree. Alright. And then the number of query is just same, nk log. Alright. Yes, you can use plotting table. Our original solution, if we don't use flying table, then we just need to update once. That's why the complexity of update is just n log, not nk log. But number of query is just same, nk log. So basically the complexity is just same. Right. Yes. So the final complexity basically same, which is onk log. Alright. Okay. And in Fenwick tree, we can also do binary search using binary lifting, or you can just use lower bound as well. Okay. So for example, if we want to find the number of prefix or just query in Fenwick tree, in the X Fenwick trees, and then we want to find the number of station that the position is less than or equal to y. Okay. So at first we want to store Fenwick trees. Actually, this is max f, and then Fenwick trees, and also the compressed coordinate. Okay. And then if you want to do query in a specific Fenwick tree, then at first we need to store the sum and also the current index, and then we will do a binary lifting in the Fenwick tree, starting from log 2x, and then until 0, and then at the id become 2 to the power of I, And then we need to check first whether the coordinate is less than y or not. And also we have to check whether id is less than the size or not. If this condition is true, so just add the sum. But if false, then just reduce the id, and then just return the sum. Alright, so in the main function, we can just iterating from f minus k until f plus k. Then we just need to query for all Fenwick trees. Right, the idea is like this. After that, just update in Fenwick tree f added by 1. Okay. Or we will add by 1 in the index xi. Okay. But we also need to pay research to find the real position here, because x is not compressed yet. Okay. All right. Is there any question for this problem? And the total memory is just on, and the total complexity, the time complexity is nk times log. All right. Okay. Then let's continue to the next problem, which is problem G. If you read this problem, okay, so actually we have to run this and also optimize this, since this pseudocode has exponential complexity. I think the worst case complexity is on times len to the power of len, since we want to check for a permutation. Of course, this complexity is so big, and also length is up to 150,000. So we need to optimize this. All right. So what does it means? What does this pseudocode means? So in this code, given two array, the first one has a length of n, and then the second one, the length is just len, and you know len is less than or equal to n. All right. And also given a value age, variable age. Okay. And then we want to do some function, or to do function to the first subarray with length n, with length len, and also we will do the second subarray, and also we will do the function to the third subarray, and so on. We will check all subarrays with length len until the last subarray, which is this. Right. And the length is also len. All right. And what function f means? What does it means? Function f is to arrays as its parameters, and in this case we will check whether there is a permutation or a matching, one versus one matching. So we will match one with one for its value in both arrays, and then we want to make sure that the sum of all pairs is greater than or equal to 8. So if this is equal to 5, and then this is equal to 4, and 8 is 9 or 8, then this match or this pair is correct. But if this one is 3 and here just 2, then this pair is incorrect. We will check whether there is a perfect matching or not. Okay. If there is a perfect matching, then just return 1. But if there is no perfect matching, then just return 0. All right. So actually, we just need to compute the number of subarray with length n, which there is a perfect matching to array P. All right. Okay. Now, is it understood? Or is there any question to this pseudocode? Okay. And do you have any idea to solve this? What do you think? At first, we want to observe function f. All right. How to compute function f faster? So, given two subarrays, yes, we can use greedy if we just compute one subarray. If we just compute one subarray, just use greedy with complexity O len. How to do that? Just sort them. Yes, that's correct. Just sort them, and then the optimal matching is just check this. Right, just pairing the max with the minimum. That's correct. And just check whether each pair is valid or not. Okay. But because we want to check some subarrays, so it means we cannot do this. We cannot use this complexity. So we need to find the other ways. Okay. At first, yes, from here we got an observation that we will sort array P. Yes, array P can be sorted. So it is easier to observe. After we sort an array P, but we don't want to sort array A, isn't it? Since we will observe its subarrays. So the order is important. So we cannot sort the array A. So if there is a subarray, if we want to create a bipartite graph, so assume if there is a pair that is valid, we will create an edge. So, you know, the edge will become a suffix. Is it correct? For each node. If it is connected with this node, then always connected with all of the right nodes. For example, this node only connected with this, and then this node on connected with this. So both of them become suffix. All right. So the next observation is for its values, just check until which node he can connect. For example, after we sort this become 3 and 5, this node cannot connect anywhere. Okay. Cannot connect anywhere. That's why just make it n+1, or maybe we can sort it in non-increasing order. So from big to small. So the edge is become a prefix. Okay, then just compute the number of connected node or the degree of each node. The degree of this is 0 since we cannot connect this with anything. And then the degree of this is 2 since I can connect both of them. Yes. How about 5? Yes, just 1, 1, and then this is 2 again. Alright. And then, if we forgot these values, we just remember these values, we still can find the answer. Is it correct? We still can find the answer based on this array. So let's check for all subarrays. The leftmost subarray is false since we cannot connect this node. Okay. And the second subarray is correct. This is true. And then the third subarray is false since the second number cannot connected with anything. And the last subarray is also true. Then the number of valid subarray is just 2. Oh, alright, this is correct. How about if we will add another value here, then the degree is 2, then is it valid? Is there any perfect matching for the last subarray? How do you think? There is a perfect matching or not? And Raja said that there is. Alright. Yes. Because both of them can connect to. So just do any connection, any pair, we always can do that. Okay. Yes, that's correct. There is a perfect matching here, so the answer become 3. So can connect to values means we can connect to node 1 and also node 2. So 7 can connect 1 and then 10 can connect 2. Alright. So actually from this array for degree array, we just need to check if it is sorted, is the value of di greater or equal to I? Alright. Is it understood? If all di in, I mean sorted di, sorted in non-descending, so di greater than or equal to I. But if there is di less than I, it means there is no perfect matching. Why? Because it means both of 1 until I is less than I. So they cannot perfectly match with 1 until I. Alright. Okay. But if di is less than I, both of di greater than or equal to I, then just connect 1 by 1. Since it is greater than or equal, so we can connect them all. Alright. I think this theory is all Whole whole theorem. Walsh-Marriott theorem. Okay. But actually we don't discuss about this since the graph is simple and not general. Alright. After that, how to check this? Do you know how to check this? Actually, since we will check all of the subarrays, so we can do sliding window. Is it correct? We can do sliding window. We will add a new one and remove the old one, oldest one, and so on. But how to check whether this array is valid or not? How do you think? Do you have any idea? So at first, since T should be sorted, yes, okay. Since T should be sorted and we cannot sort many times, so we will just store the frequency of this. So we will create another array, which is CNTT. Okay, I think Raza has an idea, got an idea. Yes, that's correct. Yes, your idea is quite same as count the number of keys. Yes, that's it. Okay, so the idea is to store the frequency of its value of t. So let's define another array, CNTT, or just make it array C. C means the number of t with that values. For example, since length is 2, so just make an array with length 3, indexed from 0 to 2. And then for this case, the CNT is like this. The frequency or the occurrence is like this. And then for the second subarray, the occurrence is like this, while the last subarray, the occurrence is like this. Okay, is it understood? All right. So it means we ignoring the order of t. We are ignoring the order of t, and we store it as a count or the occurrence, just like we want to do counting sort. So we are storing the occurrence instead of storing the original array. All right, and the idea is the same as Raza's idea. You know, in each suffix here should be less than or equal to 2. For example, like this. Here should be less than or equal to, sorry, greater than or equal to 2. And here should be greater than or equal to 1. Alright. Yes, this should be greater than or equal to 1, at least 1. And then here should be greater than or equal to 2. And here we don't care about this. Alright. And then how to check whether all of them is greater than or equal? Then the next observation is to make another array, which is the value is C1 minus 2 and C2 minus 1, like this. And then just make sure that the minimum value of this is greater than or equal to 0. Okay. Okay, sorry. I think I will I will put the scratch here. This is false. Then this is true. This is true. And then this one is false. Okay. So just like what process do, we will update a suffix. Is it correct? Or update a prefix? Yes, maybe prefix. So we will do suffix sum. The suffix sum of this array is like this, and for this is like this, and for this is like this, and also for this case is like this. All right. So it means if we update in point D, then just add from 1 to D. Okay. Just add from 1 to D. Actually, we don't care about index 0. Or if there is 0, then just continue. Just keep it, since there is no perfect matching. All right. After we create a suffix sum like this, then we want to check whether this value is greater than or equal to 1 or not. this is greater than or equal to 2 or not. If both of them is true, then the result is true, just like this. But for this case, 1 is not greater than or equal to 2, then the result is false. And for this case, 0 is not greater than or equal to 1, then this is false. Okay, is it understood? Right. After that, how to check whether both of the value is greater than or equal to that? Then in the segment tree, we will store the suffix minus this. So here the suffix minus 1, and then the suffix minus 2, the suffix minus 3, and so on until the suffix minus 9 length. Okay. All right. If both of them is greater than or equal to 0, then the result is true. But if there is a negative value, then the result is false. How to check that? Just create a minimum segment tree so we can know the minimum of all of them. So if the minimum is negative, then the result is false. And then if the minimum is positive, or must be 0 actually, cannot more than 0, since c minus len, c cannot exceed len. That's why this value cannot exceed 0. So if equal to 0, then the result is true. If less than 0, the result is false. Greater than 0, it is impossible. Alright. Okay. So in the implementation, at first we will create the array with these values. After that, we will update it one by one. We will do binary search to find the value of g, the number of degree, and then we will update to a specific degree, add them one by one. So we need which segment tree, which type of segment tree. Do we need persistent segment tree? We don't need it, isn't it? We don't need persistent segment tree, but we need which type of segment tree? The hint is we need to do range update. So just use lazy segment tree. Is it correct? Just use lazy segment tree, and we don't need persistent segment tree. So is there any question for the idea of this problem? Or let me explain you using the pseudocode or just the main function. The idea is like this. Given n, length, and age. So let me rename length become m. Right? At first, we want to create a new segment tree. St equal to new tree from 1 to m. And then for each 1 until m, we will change the value. Okay. At first, we want to update from 1 until I by -1. Do you know why? Or is it understood why we should begin the implementation with this? Yes, all right. That's great. Yes, this is the initial value. All right. Yes, you already know it. After that, we want to input array A and B. I think B came first. And then we need to sort B as well. Yes, thank you. And maybe this is one base. So for that we want to update the initial values. Okay, yes. We want to change the value become the degree m minus lower bound h. How about h? Yes. What is the effect of h here? Minus h. Is it inverted? A1 minus h or h minus a1? AI, I think. We want to find the value of b that is greater than or equal to. Okay, yes, you can do that as well. All right, then just AI. And also this this means the minimum value of AI, right? So if we use lower bound, if there is a value of I here, then I think it is upper bound. Is it correct? If there is a here or if there is a plus here, we only can connect to this. We cannot connect to a plus, but in this case we can connect to a. and the number of A sometimes more than 1. Alright, yes, upper bound and minus B plus 1. Yes, there is plus 1 here since we use upper bound and want to reduce by 1. Alright, that's correct. So let's continue. We want to update in 1 and AI added by 1. Okay, is it correct? That we will compute for all queries. Yes, that's it. Yes, just continue. Yes, that's it. Okay. Yes, that's right. And finally, we finish the implementation. Yes, that's correct. All right. Is there any question? So there is one problem remaining, and two of you, Saram and Faisal, already solved it. And again, this problem can also solve it by Fenwick tree instead of segment tree. Even maybe some of you use PPDS. Yes, that's also correct. You can use PPDS as well. And actually we can create our own PPDS using Fenwick tree. Is it correct? Yes, we can create PPDS using Fenwick tree if the value is small. For example, value in array is from 1 until a million, then we can create a Fenwick tree storing the occurrence of its values. So we can just do binary lifting to find the x value. Okay, we can insert, we can add, we can count, and we can check the index. All right. Yes. We also can use that. We can use try or just like dynamic segment trees. Right. We can use tries as well. We can use try and then each value storing the number of leaves or just the total value in the subtrees. So we can do binary search on tree. If the index we want to search is less than or equal to the size of the left subtree, then just go to the left. But if more than, then just go to the right. All right, that's correct. We can create our own BTS or just using this. In order to use this, we need to include this at first. All right, and then using namespace like this, and then just create a template like this. All right, just put this into your template or just remember it. All right. Yes, and I remember this before IOI 2018, I think, just before the IOI, and I don't use that library in IOI. All right, let's back to the problem. The problem is like this: given two permutation, and we will find the sum of two permutation. The sum of two permutation is also permutation. The result is permutation. So permutation plus permutation, the result is also permutation. What does it means? So the definition is in the description. The sum of two permutation is the order of each permutation added and then modulo by n factorial, and then we want to find the permutation in that order. All right. What does order means? The order is the order of permutation in lexicography order. For example, if we have a permutation of three integers 0, 1, 2, 0, 2, 1, and then 1, 0, 2, 1, 2, 0, 2, 0, 1, 2, 1, 0. All right. There are n permutations. Yes, that's it. The order is just 0, 1, 2, 3, 4, 5. Yes, pi minus 1. Actually, not only pi minus 1, but reduced by the number of value less than that. Okay, we will discuss it later. So, for example, in the last sample test case, 1 to 0 means the order is 3. 1 to, sorry, the order is, yes, 3. And then 2, 1, 0, the order is 5. And then 3 plus 5 is 8. But there is no egg order here, so we will modulo it with n, with 6, since the number of permutation is 6. Yes. So 8 modulo by 6 is 2. So the result is this permutation. All right. So just like the sixth permutation is like this, and then 7, and then 8, and so on. Okay. So at first, we want to make the order in form of the formula which Anik just write in the chat, because we cannot write the real value of this, since the real value is too big, which is until n factorial, where n is up to 200,000. That's why don't start using the real value. So just storing an array P. All right. Just store an array P. So, Pi is, sorry, we can check the value of P1 and then multiply it by n minus 1 factorial. Is it correct? The permutation started with 0. The number of permutation is 2 factorial, and then the number of permutation started with 1 is 2 factorial as well, and so on. So for a list of permutation with length n, then n minus 1 first permutation started with 0. After that, started with 1. All right. Is it correct? Okay. Then how about the second one? The second value in the permutation. The value is P2 times n minus 2 factorial. Is it correct? But what does P2 means? P2 is not just A2. A2 is not equal to P2, not always equal. So at first we want to check whether A1 and A2, which one is greater. For example, if A1 is 3 and then A2 is 1, then okay, P2 is equal to 1. Yes, that's correct. You already know it, the relative order. Yes, okay. So the other example, if A1 is equal to 1 and A3 is equal to 3, P2 is not 3, but actually this is 2. That's why the maximum value of P2 is n minus 1. Cannot exceed until n. Alright. And so on. And then added by P3 times n minus 3, and so on. So we will store the value of that relative order. For example, this is 4, this is 5, this is 2, this is 0, this is 3, this is 1, this is 0, this is 0. All right. And then we will do the same thing for the second array. Let it array P. just doing the same thing. We will do the same thing. For example, we will do this. All right. After that, just add them. Since we want to sum the order, and for its value, this is just a coefficient of some factorial. For example, this is times by 0 factorial, and then this is 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, and so on. And since both of them is multiplied by 5 factorial, 2 times 5 factorial, 1 times 5 factorial, so we can add it, become 3. Okay, this just add 1 by 1. After that, we can modify this array, or we can balance the coefficient. What does it means? If we got a value greater than the factorial, all right. If this is not greater 0 0, okay, just leave it. If this is 1 1, all right, just ignore it. But if here is 2 and this value is 3, what shall we do? Do you know what shall we do? Yes, just mod it and add to the previous. All right. Yes, carry to the left element. That's it. We will mod it with 3, become 0. And then this is become 4. All right. After that, 4 is greater than 3. All right. Modulo by 4 become 0. And then added by 1. All right. And this is less than 4. All right. Just ignore it. 3 less than 5. 11 greater than 6. All right. Modulo it by 7. Become 4. And then added by 1. 11 greater than 6. Sorry, greater than 7. So just modulo it by 8. Become 3, and we will ignore this carry since we will modulo it with n factorial. Is it correct? This is 1 times n factorial, but we'll modulo it with n factorial, so just remove it. Just ignore it. All right. We just care to these values. All right. After we balance the array, then just create another permutation using this value. So this is 3. After that, this is 4. But in order to find the fourth value, it is actually 5. Yes, that's it. Since 3 already chosen. And then 3 means 4. 3 means what? Do you know? This 3 means which value? 3 already used, 4 already used, 5 already used. Yes. We skip it until 6. And then 0 means 0, 0 means 1, 1 means 2, and then yes, 1 means 2, and then the remaining is 7. Okay, is it correct? All right, then finally just output this permutation. Okay, I think you already understand it. Okay. So if you want to implement, you can use Fenwick tree. So in order to check what is the relative order, for example, 7, what does 7 means? Just query here and count the number of occurrence here, the sum of this prefix. So it means 7 minus 2. So the relative order is 5. All right. This is when we want to find the order. And then when we want to find the result permutation, then we can do binary lifting until we got the exact values. Or yes, maybe you can, yes. Okay, you can use segmentary and we can use bandwidth tree as well. Okay, yes. So the bandwidth tree. At first, let's create an array for Fenwick tree. Then create a query function. Yes, all right. And actually, the value of x is only between 0 or 1, never greater than 1. So it means if OPI greater than or equal to M, just OPI minus 1 plus plus. And this is also correct. And okay, you cannot do this for the second case. Ref is only for finding the order. Okay, so just just create function to find the order. Yes. Okay, we need to create update function as well. Yes, you can create the update. And then I also need to create another query function. I think this is less than or equal, maybe. Okay. Yes, that's also correct. Yes, this is just same as I plus I n minus I. Yes, I can prove this as well. All right. So just continue to write the order procedure, and I will create a function to use query. All right. In order to find the answer, we also can use this. We can, at first, we want to reset the bandwidth tree. And that we want to update all of them. Set all of them become true. And then we will do query OPI, and then just output X. After that, just update index X with -1. All right. This is how to find the result using bandwidth tree. And the query function is different with pref. Pref means the prefix sum, but query means we want to find the X value, X active value. So after we use X, then just deactive X. So we will skip X. All right. The query function is different with prefix function. The query function is like this using binary lifting. and prefix function is like this. All right. Do you know about this trick? This is how to do binary search in bandwidth tree with overlap and complexity. Okay, that's good. Okay. Is there any other question? I think that's all our discussion about the second exercise. And then for the next meeting, what topic you will discuss in the next week? Do you have any suggestion or idea after the vacation? All right. So how long your holiday is? Until which date? Until next year, I think. Okay, 2 weeks. Yes, until next year. Is it correct? So you are doing vacation 1 year until next year. Okay. Yeah. So just have fun and still keep studying. Don't forget to always preparing for IY. You can reduce the frequency or reduce the study hour, but don't stop studying. Okay. Yes, thank you very much. So that's all for today. Let's close our meeting with praying kafaratul majlis. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Wassallallahu ala nabiyyina Muhammadin walhamdulillahi rabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh.